Continuous basalt fiber is essentially the same chemicals and minerals that are put together to produce the white fiberglass that we're used to. The difference is that there was a mixture produced in the Earth's core under heat and pressure that's very financially difficult to justify in industrial chemistry. These minerals were mixed for potentially hundreds of thousands of years under fantastic pressure before they came out to the Earth's surface in a volcanic lava flow. The end result of being mixed that long under that kind of pressure gives us a material that's about 30% better physicals across the board. It has some other interesting characteristics in that it's immune to UV. We're doing a lot with it in the solar industry and the wind industry because it can be outside unpainted and not deteriorate. As I said before, it's totally non-rusting, it's non-magnetic, non-conductive. Continuous basalt fiber has been through a complete battery of toxicity testings. Years ago, when the friction industry was looking for a replacement for asbestos because of this mesothelioma issue with lung cancer, they discovered basalt fiber. And you're probably around it every day and don't realize it. The brakes on most cars today are basalt fiber. It's able to take heat and pressure and cyclical motion and vibration actually better than the asbestos that it replaced. While we're talking about basalt and its characteristics, obviously if it works in cyclical motion and for things like brakes, it's a very tenacious material. That's one of the most exciting things about this is its ability to take abuse. We talked earlier about, let me start with steel. Okay, so steel is a 40 to 60,000 psi tensile material, and it has a modulus of 200. We're going to just use this as a baseline. Everybody knows about steel, you know its characteristics, how it feels. It's ductile. When you bend it, it takes a set and it stays there. Well, we don't have that ability with composites. Composites, once the fibers are set, they want to stay straight. You can't bend it. If there's a downside to it, you can't bend that on the job. We're going to get into how we deal with that in a minute, but for right now, I just want to discuss the differences and the advantages of that composites do have, and what the advantages of rock rebar are over carbon fiber, which I'll show you. We've got a piece of carbon fiber over here, really expensive, 20 to 30 times more expensive than fiberglass, and of course much more than steel. Fiberglass has a tensile strength of actually more than twice what steel has. Steel is 60, fiberglass is 120. Where fiberglass is potentially a little bit weak is in modulus. Steel has a modulus of 200 gigapascals. Fiberglass about 50. And you can demonstrate that in that fiberglass is quite flexible. It has a little bit of early bend and early stretch. And when you use fiberglass for composite or for concrete reinforcement, you have to be sure to use enough of it because it also has an elongation of about 4.7 to 5.7% elongation of break. That means for this diameter, it would actually stretch about, we'll call it 5% of the diameter before it parted or ruptured. So you're going to get a little bit of flex in the panel. If you move the material out closer to the surface of the panel, which you can do because it isn't going to rust the way that steel did, you get it further out on the bend moment and it stiffens the panel back up. The fiberglass is a little bit more brittle than basalt. You watch, I bent the steel, and this quickly bends quicker, and if I push on it hard enough, it will rupture. Basalt is a bit more tenacious than that. That's about the same length as that one. I can't even think, you can clearly see that it doesn't even want to begin to bend early on as much as the fiberglass did. That's because its modulus is 100. Again, steel was 200, fiberglass 50, basalt 100. With the epoxy and urethanes that we use, depending on which version of rock rebar it is, we do get a stiffness of about 110. So we're quite a little bit better than fiberglass. I'll do some smaller materials. This is a piece of, this is 6 millimeter, and at this level, not only will it not break, it'll bend. The swimming pool guys love this because you can see that it would make a really nice corner for a pool. You don't have to play games with bent steel. The little 4 millimeter, this is as small as we produce it because you can tie this stuff in a knot. It's an extremely tenacious material. The larger sizes, this is 12 millimeter. Here's a little bit bigger than a number 4 that you're used to for steel. Extremely stiff. Once we get past this size and we produce rock rebar up to 1.5 inches, here's a piece of 1 inch. This is a real hoss. This would be easily replace 1.5 inch steel if you ever got in anything like that. You are much better off to use more smaller sizes in composites, and that's true for rock rebar, it's true for fiberglass, and it's true for carbon fiber, to get better surface contact. All these composite materials are so much stronger than steel that they easily overpower their grip. Eventually, if you push on something with a composite reinforcement, it's just going to slip it. That is the reason that we put this fiber winding on here. Someone asked, well, what is this white fiber wrapping this up? That's causing a shape change so that the concrete gets down in it and gets a grip to it. The same way with steel rebar, the hash marks are the shape changes on the steel. Again, since I'm holding this up there, you can see this piece is rust, and that rust is going to grow and split the concrete open. We do not have that problem with composites. Let's move over to a table and sit down and get into a discussion about what we do about bends. Okay, continuing. When I left off, I was discussion about bends. Everybody wants to understand bends. You can take steel and bend it. Takes a set. That's it. It'll hold the shape of a cage roughly. As I said earlier, if it gets too close to the edge of the concrete and goes through, or is just too close where it can wick moisture in, you have a rust issue. Getting into composites, you completely eliminate that, but you also eliminate the ability to bend the material. We do make bends. The composite industry makes bends for use in structural materials for concrete. Traditionally, those bends have emulated steel. Piece of number 3 steel, piece of number 3. This is a real old piece of rock rebar when we used to bend it this way. There's should be a piece of fiberglass rebar floating around here. Also, the same bend. This is traditionally the way the industry has performed a composite bend. The problem with it is that when the longitudinal material is inside it and it's tie wrapped, it fits very poorly. So consequently, when there's pressure to hold longitudinal material from buckling, and that's the purpose of the lateral material called stirrups, which are used to keep the longitudinal material from buckling, keep it in line. When it fails, predominantly it fails in the corner because the corners are weaker. If you refer to a document called the ACI 440, which is at this point the Bible on composites reinforcement for concrete, it says right in there that the corners are much weaker than the actual straight material, and they're quite correct in that. If you're
producing the bends the way it's traditionally been done. At Raw Orange Materials, we got away from that because we can. We have some machinery that allows us to do high-speed wraps. In the stirrups that you see in steel, there'll be 4 corners, but the 4th corner there's an overlap, and I'm sorry I don't have a complete stirrup around here, but most people in this room probably know what a stirrup looks like, where the bends return to the center, unless it happens to be a welded stirrup where they put it together. At any rate, the problem when you go to composites is that the fibers don't really want to make that corner if they're being run in a pultrusion process. And if the manufacturer is making a pultrusion, all the fibers are being pulled out of a machine that, we'll call it 1,000 pounds of pressure, being drug out of that machine in perfect parallel, having been coated with resin material and headed towards a heater system that's going to solidify that resin into a solid rod. Well, to make a bend, what they do is before it goes to the heater, they wrap it around a mandrel. You can clearly see how that's happened in this piece of fiberglass rebar. Well, that creates a whole bunch of problems. I'm going to demonstrate what it does with using a stack of paper. The fibers in that stack, when they make a corner, one's going to be on top of the other. They can't all be on the same plane. If that were the case, it would be laid out flat. Obviously, that flat corner is going to be very weak and fragile. You're not going to be able to ship it. It's impractical. So they just assume that these things can bunch up, and that isn't good physics. Here's what happens. With the edge square here, and I squeeze this paper, and pull on it the same way that the machine would be pulling the glass fibers to make the rebar and then make the bend. When I bend it, look what happens. It puckers up. The outside's stretched taut. Well, the inside's too long, so it bulges out. And that causes a really, really weak corner. There is only one piece of paper in this whole stack that's truly unloaded and in neutral position to take weight and load in this stack of paper. If I let one end of it go and fold the corner, look how beautiful that lays out. But look how how uneven the threads are, and that's the problem with making corners with the pultrusion process. We don't do it. Our high-speed winders were able to take the fibers and wrap them around a set of pins. This is a rock stirrup. This one happens to be, I think, for 25 millimeter, just a little 6 by 10 cage for some beam somewhere. We take the roving as it is in this state, and it's coated through one of the high-speed coaters, and it goes on a set of forms, pins, and it's wound around the pins. Really simple in principle, very difficult to do at high speed. We are able to put a stack of rovings around these pins to produce these stirrups to get whatever strength it is that's required for the application. Well, the beautiful thing about it is, since all those were wrapped, they were wrapped like belts of a tire or belts of a lifting strap that we all trust. There are multiple layers, and each layer is taking the forces balanced. If I put a piece of rock rebar up into it, here's this little 25 millimeter piece will probably suffice to show you how perfectly it fits. Concrete will get down in that area, and it's perfectly saddled. There is no movement, and in a case when forces are applied to it, the fibers are already laid in the position in which they want to be in to carry the load. They don't have to be stretched and pulled out of position the way they would be in a situation where this piece of 25 millimeter or 1 inch rebar is wrapped by this 2 inch piece of a stirrup. When the fibers are coated, they're solidified into a solid. Now this solid is it's called an anisotropic material. That means that the strength of the material is with the length of the strands.
Steel bends and maintains its strength through the corner because it's an isotropic material. It means that its strength in all directions are the same. Fibers, whether they're carbon fiber, fiberglass, basalt, Kevlar, are anisotropic materials. That means that their materials are just in the direction of their strand. Use a piece of carbon fiber here because it's readily available. Most of the strength of this material is longitudinally with the grain of the material. You can easily, in this state of roving, pull it apart. There's obviously no real strength there. When it's bonded together in an adhesive matrix, and the adhesive matrix could be vinyl ester, polyester, epoxy, urethane. At Raw Engine Materials, we only use epoxies and urethanes. As I moved over to this side, someone has asked what this piece laying against the wall is, and since it's the backdrop, I'll get into answering that question right now. After we learned to coat continuous basalt fiber with the adhesive matrix at high speed, it's opened up a whole lot of possibilities for different things that you can produce. In a street, you might have a steel wire, a welded wire. Well, we're able to do it now with non-rusting continuous basalt fiber. This part is actually called rock DNA. It's an item I invented and patented. It's licensed to another company right now for use in reinforcing pervious concrete. If you don't know, pervious concrete is a Portland product that was developed. It's about 25% open, so if you pour water on it, it goes right through. And it's a great way to deal with water retention issues. You don't have to worry about storm sewer systems near as much because the water simply passes through the concrete and goes into the water table. Well, and it's a big leads thing right now. Green projects are huge on pervious concrete. The problem has traditionally been with pervious concrete, you couldn't reinforce it with steel because if it was 25% open, obviously the steel's exposed immediately, so it's going to rust immediately. The main way that they reinforced it was with fiberglass and various kinds of emulsions. This is an emulsion that we produce for pervious concrete, where we suspend the rock staples in it. You can see how well everything stays in suspension in this liquid. And it does a remarkable job of reinforcing pervious concrete on its own. And again, the advantage to continuous basalt fiber staples, rock staples, over fiberglass is the elongation that these will experience before they would actually break or rupture is only 3%, which is exactly the elongation of concrete in its natural bending before it splits. The fiberglass versions, Fibercrete, the fiberglass in them is actually going to have to move 5% before it fully loads up. Well, the concrete already broke because the concrete broke at 3%. The fiberglass isn't even fully loaded up until 5%, so you have to use a lot of it. By going to rock staples, since rock staples are 3%, concrete's 3%, everything balances out perfect. Coming back to this rock DNA, even with rock staples in there, if you're going to run a fire truck over it or it's just a cement truck, something heavy, this isn't going to hold it, not impervious concrete. So how do you reinforce it? Well, what's been done before the advent of rock DNA was just make it thicker. Obviously that takes the economy of scale out of it because now you need perhaps as much as 16 inches of pervious concrete to make it structural enough to hold a fire truck. Well, with the advent of rock DNA, we can go in at the bottom of the slab, at the bottom of the bending moment, and right above the road bed, apply a layer of rock DNA, and the concrete, when it's poured, goes through all these holes. Well, because it goes through the holes and it gets to these intersections, it's mechanically locked. We don't have a slip issue. This is not relying on the adhesion, the bond strength to the pervious concrete, not really at all. It obviously does for some portion of time, But in the event of a one-time overload, like a fire truck ran over it, let's say that it did crack the pervious concrete, this material carries that load like a trampoline. The tire print of the fire truck pushed on it, those loads were dissipated laterally out to the perimeter. There was a deflection, possibly it popped the concrete, but as you have seen with the resilience of continuous basalt fiber, it just pulls back. There's a single strand of rock DNA here, which we sometimes use for headers, where you're worried about slippage, where we really want a lot of potential to carry tensile loads. Well, if this was it would actually lay down in the header, but when it's laid down, the concrete pours through it, and these edges are actually interconnected. The fibers pass through each other, and they're mechanically locked in there. This can't be separated. While we're on the discussion of grid reinforcements, this is a material that we make called rock mesh. It's simply the roving glued and stitched together. Makes a really great non-rusting reinforcement for things as thin as a countertop to as thick as a sidewalk. What you would use a material like this. We make it, this is 1x1, we make it up to 2x2 and then down to 1/8 inch. Here's a piece of rock mesh that's 1/4 inch. This material was something that was developed for SIP panels, structural insulated panels, mag board, MGO board. That industry had an issue with their MGO board was so strong that they had a difficult time taping the joints. It exceeded what fiberglass could do in tensile when they had thermal swings. So we developed a tape made of basalt, and basalt being stronger and having better adhesion to the cementous materials than fiberglass solved that problem. Just left off discussing how rock DNA prevents slip by mechanically allowing the concrete to pass through it, and the intersections here are actually intertwined and locked so that the fibers are braided through each other to prevent any kind of shear or peel. In conventional rock rebar or conventional composites, in any case, pull-out is an issue because the materials are inherently so much stronger than steel. Steel's been worked out to be 40, 60,000 psi, and they've got their hash marks on it to prevent pull-out and achieve an ultimate bond strength. We designed rock rebar with a Dacron, or actually we use fiberglass so that we can see it real easy, to squeeze down on the basalt fibers and epoxy as it's made to cause shape changes. The winding doesn't really have anything to do with the strength of the bar, but what it does do is force these shape changes and allow concrete to get in here and get a grip on it. And we have it worked out with the spacing and the depth of these to where we get a really good bond strength. If you're going to overlap two pieces of rock rebar, you want to do it about 20 diameters of the bar, and you're going to achieve in concrete sufficient pull-out to lap from one to the other. On the screen here is a beam test that goes a little ways to showing you the potential that rock rebar has to stiffen something in its tenacity. This beam has 3 pieces of 8 millimeter. 8 millimeter is a little smaller than number 3. Number 3 is like 375 thousandths of an inch. This is 352 thousandths of an inch. And 3 pieces of this are buried in this thing, 1 inch from the bottom, middle, and an inch from each edge. He's applying a tremendous amount of load to this, and you can see how much deflection there is in this beam. And the kid that's doing it's grinning because he's so impressed how much bend there is in this piece of concrete. When we take the load off of this concrete is going to return to straight. But it continues to apply a load to it. Now it's bent and it has failed, but look what happened. It did not break or separate, part, or rupture the continuous basalt fiber or rock rebar in the bottom of it. It crushed the concrete in compression. The bending force on it overloaded, exploded the concrete on top. I believe there's a shot right after this one where it's the baseline test for the rock rebar was performed that went in this beam, so we knew what we had to work with. This is this piece of 8mm. That's 18 inches in between here, and there are 18 inches of material buried in these pipes in an epoxy compound. Rock rebar is so strong that to grab hold of it with collets the way that conventional steel rebar is done, it easily exceeds what the collets can do as far as grabbing the material. So we have to epoxy it into the pipe of a much larger size to get a pull on it. This little green device right here is testing for Young's modulus, and in the picture right after this, you're going to see what it looks like when it ruptures. It's failed. It's been pulled on now. That was around 160,000 psi of pressure was put on that material, and the failure was not straight across as you would expect, or not straight across the way that you would see steel fail. It actually sheared the fibers, but it sheared the resin holding the fibers together. Technically, this is more a test of the epoxy holding the fibers together than it is the fibers. But the point is that in a failure, the failure is very spread out in rock rebar. Okay, as I said earlier, President Obama wouldn't loan me the teleprompter, so we're winging this. I want to make sure that we get everything covered. I'm going to have to take this disc to the airport so it gets there for your conference. We discussed a little bit about the rock rebar and the windings, and I believe I covered that if you're going to splice sections together, you want to do it at 20 times the diameter. That's your overlap between two pieces of rock rebar. Cages and stirrups and corners. I've explained that there is a method that we deal with the corners. We can make round corners if you want to. You want corners that you want to splice in fine. We'll send you squares. You can trim them here, trim it off at the corner. Now you have a corner that you can splice to a piece of rock rebar at 20 times the diameter, and create yourself a corner there. That's one way. A lot of the things that you'll be able to do for precast, we can make you the lateral cages and stirrups. This is roughly an 18 by 18 for something. We make them up to 8 feet by 8 feet, or rectangles. We make oddball shapes like this. This was a cage for a parking garage pillar. We make things for pilings. This is this little thing I've got tilted in the chair here is just a little cage. People say, well, how do you fasten it? She can zoom in here. You see this is done with tie wraps. You can do it with the steel wire twist guns, or just plain old wire twists if you'd like to. You can mix rock rebar and steel cages if you want to, but we did that for a long time because we developed the rock rebar before we actually went to the cages. In a minute I get into explaining the philosophy of how the stirrups are produced, and that they're wound as opposed to bent. That's coming up here in a middle. I want to be sure we cover the actual rock rebar itself. When we run it, it's a continuous, constantly coming out, running. A master coil's around 9,000 feet long. These are 650 feet. This is 8mm. This is 650 feet, probably weighs, I think it weighs 50 pounds. Here's a little coil of, that's number 6, or 6mm, excuse me, not number 6, 6mm. This one is 10. We coil it up to 13 millimeter, or number 4. We can do put 5/8 in there, but it's a giant spring. Once we go past 13 millimeter or number 4 bar, half-inch bar, it'll go to 40 foot rods. Maybe some special occasions. We do a lot with seawalls. Big long seawall cap. We can run 9 strands of 12 millimeter down that. There's no splices. Bam, bam, it's over with, and never have to worry about the rust or anything popping through. Since this is in front of me, the stirrups. If you were going to make a lot of cages, we adjust the pins on our machine to run you the stirrups at whatever size you want, length and width, and then wrap them. You'll take and drop, punch the rebars through it, and then spread them out. Just cut the shrink wrap off, spread them to the corners, and tie wrap them. Just really simple. It's much faster than dealing with steel. We make a number of really interesting parts other than composite reinforcements. Let me get over here. By the time this is all done, I've worked myself right out of the building. Continuous basalt fiber can be run really smooth and beautiful. We're getting into window frames, door frames, solar panel frames. The thermal insulating qualities, the fact that the expansion characteristics are the same as glass. We can also do, well, this is a piece of extrusion. It's such a tenacious material. This is a replaceable blade for a diesel boat, one blade of 6. Here's a section of a wind turbine blade. It's unbelievably strong, and it weighs nothing. This weighs like a pound a foot. It's an incredible thing between fiberglass. When fiberglass is not strong enough and you can't justify carbon fiber, continuous basalt fiber is the answer. Let's go back over here and cover, since you're in the precast business, there's most of you have probably heard of a material called geopolymer. We're heavily involved in geopolymer. Geopolymers are amazing cementous materials produced at basically boiling water temperatures as opposed to 2400 degrees to make clinker. This is this one's probably 50 pounds a cubic foot. This is been somewhat lightened, probably 90 pounds a cubic foot. The material is so tenacious that you can drill and tap it, and all this is reinforced with the continuous basalt fiber staples. Where did our little bottle go? These are the staples, similar to what you would put used to putting fiberglass for fibercrete. That's rock staples. They're a little bit different shape, and they have a little bit of a different coating on them for good adhesion to the cement. This is I may have shown this before in this video, but they're floating in a polymer that then goes into the geopolymer cement, and this will also work in Portland. Instead of fibercrete, you'd be basaltcrete. The tenacious nature of the material. This happens to be a part for a mount for a solar panel, and instead of producing it in steel, we make it in basalt, and this is much less expensive than steel. Never ever rust, impervious to UV, and makes a really interesting part that goes on a solar panel. Channels, different thicknesses of parts that can be produced with the material. There's a lot of things that we can do with it. The key was our methodology of coating the basalt fibers to be able to run them at high speed. I want to say a little bit something about concrete and steel. We've been putting concrete or steel and concrete to reinforce it for, 100 years, getting exactly the same results. Steel rusts. When it rusts, it swells, causes what we call spalling, splits it open and fails to part. In this day and age, with the internet and the ability to communicate, it's easy to find data on the millions and millions of dollars of testing that's been done on steel and concrete, all of which conclusively prove that steel rusts. All the galvanizing and zinc chromating that's done are all band-aids. They're all treating the symptom of the cause. The cause is steel rust. It doesn't belong there. Composites are destined to get into civil engineering, building, precast industry, the same way that they now are beginning to dominate aircraft. Before that, it was the marine industry with boats. Composites offer a tremendous advantage over steel. They just need to be used the right way, and people need to be educated on them. We all know that the civil engineering community, the building community in general, are very risk averse. And I believe that the best way to sell our products, the products of composites, into that industry is to use the risk averse nature of this conservative industry to help us sell. It could be argued that it's much more litigiously irresponsible to continue to put steel and concrete getting the same result. That's more important than the risk aversity of somebody not wanting to change because they're afraid they'll make a mistake. It's time that they get off the fence